Hello everyone, welcome back to Math with Allison. Today we're continuing our integration series, so we're just going to go ahead and evaluate some definite integrals. So let's go ahead and dive into it. We are using the Fundamental Theorem of Calculus, which says if f is continuous on AB and capital F is any antiderivative of f on AB, then when we take the integral on a to b of f of x, we first take the antiderivative, so we get capital F of x, but we're still integrating that on the interval a to b. So what we do is we plug in the upper value and then we subtract the lower value plugged in. So let's go ahead and just dive into it. Our first example is we have the integral from 0 to 1 of the square root of x minus x. I drew out a picture of what we're actually doing here, and we are finding the area between the two lines. So why do I know it's the area between the two lines? Let's go ahead and take an example of rectangle. So here is my little rectangle. We're taking our upper value, which is the square root of x, and that gives us the entire length. But we are subtracting off this little length right here because we will only want to deal with this area. So this little length is x. So that's why we get the square root of x minus x. And we're doing that all the way between 0 and 1. So let's go ahead and do this thing. The first thing that I'm going to go ahead and do is rewrite this as x to the power of 1/2 minus x. That way I know I can use power rule. So let's do that. We add 1 to the exponent, so I get 3/2, and I divide by that new exponent. And now we're going to do the same thing for x. So we add 1 to the exponent and we divide by that new exponent. And we're still doing that from 0 to 1. I'm actually going to rewrite this before I plug in those values. When we divide by a fraction, we multiply it by it flips. So we multiply it by 2/3. Okay, let's go ahead and plug in the upper value. So when I plug in 1, I get 2/3 times 1 to the 3/2 minus 1 squared divided by 2. And now I'm going to plug in my lower value. So here I get 2/3 times 0 to the 3/2 minus 0 squared divided by 2. So now when I multiply that out, I get 2/3 minus 1/2, and then this whole thing goes to 0. So let's go ahead and create a common denominator. I'm going to multiply this by 3/3. I'll multiply this one by 2/2. So here we get 4/6 minus 3/6, which is equal to a value of 1/6. So here we have our area. This little guy right here has an area of 1/6. Okay, so here we have another one, the integral of 0 to pi over 4 of that whole thing. So my first order of business is I'm just going to go ahead and multiply that secant of x in. So secant times cosine. So secant is 1 over cosine. So 1 over cosine times cosine is equal to 1. And this we can take the antiderivative of. So let's go ahead and do that first. The antiderivative of secant squared is tangent of x plus, and now that becomes an x from 0 to pi over 4. So let's go ahead and plug in our value. So I'm going to go ahead and do upper first. We get tangent of pi over 4 plus pi over 4. And now let's go and subtract our lower value plugged in, tangent of 0 plus 0. These work out nicely. This whole thing goes to 0. We have tangent of pi over 4 is equal to 1 plus pi over 4. I would say just leave it like that. Let's go ahead and try an exponential function. So here when we take the antiderivative, the 10 is a scalar multiple, so it just hangs out. But when we take the antiderivative of e's, first we have it remains the same, but we divide it by the derivative of the exponent. So the derivative of 2x is just going to be 2 in that case. And we're integrating this between 0 and 1. So let's simplify that really quickly. I know this divides out to be 5. So we get 5e to the 2x, and we're integrating that between 0 and 1. Now we can do upper minus lower. So we get 5e to the power of 2 minus 5e to the power of 0. Don't forget, e to the power of 0 is not going to go to 0. That's super common because sometimes our brain just does that. But this actually becomes a value of 1. So we get 5 times 1, which is equal to 5. And this right here is our solution. Here we have an inverse trig function, so let's go ahead and find the antiderivative. 1 over 1 plus x squared is going to be inverse tangent of x, and we're integrating between 1 and the square root of 3. So let's go ahead and plug those in. I have the upper minus the lower, so inverse tangent of 1. So remember, this is going to be the angle at which this occurs. I drew out my little triangle right there. So I want the angle for which tangent is equal to the square root of 3. So I know that occurs at pi over 3. And I know that tangent is equal to 1 at pi over 4. So here, if you wanted to combine these, you could do 4 pi over 12 minus 3 pi over 12, and this is going to give you a value of pi over 12. And that is our solution. Here we have a fun one. We got another trig function. So let's go ahead and take the antiderivative. That 8 is a scalar multiple, so it just hangs out. The antiderivative of cosecant squared is going to be cotangent of x, but it has to be negative because the derivative of cotangent is negative cosecant squared. And this we're integrating from pi over 4 to pi over 2. So let's go ahead and plug in our values. First, we have negative 8 cotangent at pi over 2. And we're going to go ahead and subtract negative 8. So that becomes a positive 8 cotangent, and that is pi over 4. So this one is very nice. If you don't remember what, cotangent and cosecant, all those things do, just write it in terms of sine and cosine. So I'll go ahead and do that for this one. I know cotangent is going to be cosine of pi over 2 divided by sine of pi over 2. And I know cotangent of pi over 4 is just equal to 1 because cosine and sine are the same at pi over 4. It's the square root of 2 over 2. So let's go ahead and remember cosine of pi over 2 is equal to 0. Sine of pi over 2 is equal to 1. Plus 8 times 1, which is 8. Now this whole thing isn't being multiplied by 0, so it just goes to 0, and we get our solution is equal to 8. Okay, so we got one more here. I'm going to go ahead and separate this into two separate fractions. And so here we have the antiderivative of 4 over 9. And I'm going to go ahead and rewrite this. This is 2 times 1 over t. And this goes down to t to the negative 1/2, right? If we simplify that, this is going to be t to the 1/2 divided by t to the power of 1. When we subtract the exponents, this becomes t to the 1/2 minus 1, which is how I got negative 1/2. Okay, let's go ahead and find the antiderivative. So first, that 2 is a scalar multiple, so it hangs out. And the antiderivative of 1 over t is the natural log of t. And now what we do is we add 1 to the exponent, so that becomes positive 1/2, and we divide by that new exponent. And this is being evaluated from 4 up to 9. Let's go ahead and take one more line to rewrite that. We got 2 times the natural log of t plus, and now when we divide by a fraction, we multiply it flipped. So that becomes 2t to the 1/2, or if you wanted, you could rewrite that right now with the square root. And this is from 4 up to 9. So let's go ahead and plug these in. We're going to do upper minus lower. Okay, so what I'm going to go ahead and do first is exponent rules for natural logs. So that means this 2 gets to come up as the exponent for the 9. So that becomes the natural log of 9 squared plus 6 minus the natural log of 4 squared plus 4. So let's go ahead and add that 6 and 4 together. We get the natural log of 81 minus the natural log of 16. So I'm going to go ahead and use another natural log rule. When we subtract natural logs, really what we're doing is we're dividing them. So that becomes 81 divided by 16. And I don't know any common multiples between 81 and 16, so I think that's as simplified as we're going to get. So that is all I had for us today in this video. If you enjoyed it, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.